In this video, we will deconstruct standards EE3 and EE4 of the Grade 6 Georgia Standards of Excellence for Mathematics. Standard 6 EE3 requires students to apply the properties of operations to generate equivalent expressions. For example, apply the distributive property to show that 3 groups of the sum of 2 and x is equivalent to the sum of 6 and 3x, and that 24x plus 18y is really the same as 6 groups of 4x and 3y. Combining like terms also comes into play, for instance, to demonstrate that y plus y plus y is the same as 3 times y or 3y. And Standard 6 EE4 asks students to identify when 2 expressions are equivalent. So instead of generating equivalent expressions, here students are expected to determine whether given expressions are equivalent or non-equivalent. These 2 standards are not limited to symbolic representations only. In fact, it's critical that students connect multiple representations, especially concrete like algebra tiles, and pictorial, such as area models, to the expressions and equations they encounter. This cluster of standards represents a landmark in the journey towards success in algebra. Think for a moment. Why is it that so many students do well in math as young children, but then hit a wall in algebra? Well, research says that for most of these students, their struggles with algebra stem from not making connections between algebra and arithmetic. Fortunately, our standards require students to begin making these deep and explicit connections early in their elementary math experiences. How so? By making sense of number operations through applying the properties they'll need to be successful in algebra, instead of just mindlessly memorizing procedures and algorithms. It's our first mathematics practice standard. For instance, maybe you've questioned why students learn multiplication strategies like partial products in 3rd and 4th grade. Well, the reason is simple. According to curriculum experts, it's because students who can break expressions apart to find products like 5 times 37 into 5 groups of 30 and 7 and see that the product is 150 plus 35 can now see that 5 times the quantity 3a plus 7 is equivalent to 15a plus 35 for all numbers a. The bottom line is we are bridging the gap between arithmetic and algebra. So in this video, you'll notice a strong emphasis on visualizing, reasoning, and sense-making strategies to bridge this gap. Speaking of videos, if you're curious to see what kinds of experiences students gained with properties of operations, check out the first grade video on Standard 1 OA3. In grade 1, students applied the commutative and associative properties of addition to add numbers. In grade 3, students applied the commutative, associative, and distributive properties to make sense of multiplication. As far as exponents go, students worked with powers of 10 within the context of base 10 place value in 5th grade, so they'll have a little prior knowledge with exponents. But of course, there's a grade 6 standard, 6EE1, that provides further extension with whole number exponents. And as far as writing and interpreting numerical expressions, students got a heavy dose of that in 5th grade, and they even formally explored the order of operations. Check out the video on 5 OA1 and OA2 to learn more. So vertically, a nice progression exists between 5th and 6th grade because students worked exclusively with numerical or arithmetic expressions in grade 5. And in grade 6, they will build on this work with algebraic expressions and equations. One of the first considerations in planning effective instruction should be to connect new content to the student's prior knowledge. Previously, students will have expressed the sum of 2 numbers using their greatest common factor in the distributive property. And this open middle task allows students to use critical thinking to generate 2 equivalent expressions using the digits 0 through 9 no more than once each. Listen to how this student uses number sense and reasoning to generate a solution.
A number, you would only have a 1 digit here. So I went up to the next digit, which would be a 2. But you want a smaller number, so when you multiply these 2, you still get a 1 digit. But when you multiply these 2, you get a 2-digit number. So I wanted a low number right here, so I stuck 3, which would be the next number. So when you stick 3 here, you get 6, and then I just added 9 because that works.
Like most concepts, providing a concrete representation in the beginning will help develop conceptual understanding of the idea of equivalent expressions. One way to accomplish this is to have students measure shapes using paper clips, like this triangle, for example. Lay paper clips around the edges of the triangle with no overlaps or gaps. We can see that this side of the triangle can fit 1 paper clip the long way and 2 paper clips the short way. As we continue this process, model the perimeter with an algebraic expression where L represents represents the number of paper clips in the long orientation, and S is the number of paper clips in the short orientation. In the end, it is easy to see that the perimeter of this triangle can be expressed as 1L plus 2S plus 2L plus 2S plus 2L plus 1S, or in simpler terms, 5 longs and 5 shorts. To extend this idea, measure regular polygons in the same fashion, like this pentagon. The length of one side is 1 long plus 2 shorts. And since this is a regular pentagon, the other 4 sides are the same length. So rather than counting all of the paper clips, we can express the perimeter as the total number of sides, 5, times the length of each side, 1L plus 2S, or in simpler terms, 5 longs and 10 shorts. Through repeated examples, students should discover the shortcut using the distributive property. Working with abstract representations for expressions and equations will not result in conceptual understanding of algebra. Therefore, it's important for students to connect algebraic expressions to pictorial representations like area models. Pictorial representations are so powerful because they help students to clarify their own misconceptions. Case in point, watch how this student self-corrects her own mistake by drawing a picture of her expression. Prove that 4 times the quantity 5 minus x is the same thing as 4x minus 20.
So if I were to draw a diagram,
Okay.
so this would be 4, and then the total would be x,
Okay.
and then 5 would be here.
What does the 5 minus x represent in your diagram?
The 5 represents the perimeter of the width of the
Non-shaded part?
yeah, and then the x represents the width of the total thing.
Okay.
So to find the area of the non-shaded part, you would have to find the area of the shaded part and then subtract it.
How do we know how long this segment is?
Times
You
How long is that?
7, yeah.
it's 4. It's x minus 5.
Oh, okay, x minus 5.
Oh, so this would be. Let's see.
Okay, so why'd you change that?
Because since to find the non-shaded shaded area, we would have to do x minus 5 because 5 minus x would mean we weren't finding the area of anything.
This student has taken ownership of a common mistake without ever being told by the teacher that she was wrong. By simply asking her, what does the 5 minus x represent in your diagram, she has made sense of the mathematics for herself. How many shaded squares are in this 10 by 10 grid? Do not count them one by one. Pause the video here and reflect on how you grouped the shaded squares. This is an adaptation of a Marilyn Burns task that we use to help students connect pictorial representations to expressions, first arithmetic and then algebraic. To begin, simply record students' thinking as arithmetic expressions. For example, this student sees 4 groups of 9.
4 9s.
Oh, so you're telling me that you're seeing 4 9s. Can you walk up to the board and just kind of show us the 4 9s that you're seeing? Because you're onto something.
9 9 9 9.
Next, watch how the teacher presses students to make connections between the various expressions for counting the 36 squares.
Go ahead.
It's like the first one, but instead it's 10 times 4 minus the 4 corners.
Okay, good. So the -4, the darker maroon color, is subtracting the 4 corners. But if you remember the first slide, what's the difference in this representation? Jaylee.
Well, in this representation, instead of subtracting the 4 corners, it's not counting it as 10, it's instead counting it as 8 and then adding the 4 corners.
Very good. So we had 8 groups of 4, and then we added the 4 corners this time.
After students have had plenty of time to discuss how to represent different ways of counting the 36 squares with arithmetic expressions, it's time to algebraify them. We'll let the variable h represent the height of the square grid, and push students to transform their arithmetic expressions into algebraic expressions.
H is 10, which there's 2 10s, which is 8 plus h, and 10 minus 2 is h minus 2, which is 8, and which is 8 minus 2 plus h minus 2.
Okay, so the h minus 2 corresponds to which color?
Blue.
The blue. Okay, and what about the h?
The h responds to the red.
Very good.
The h is the red.
Watch how these students use the diagrams to make arguments and critique each other's reasoning.
So then down here you do h take away 3.
No, I think it's h take away 1 because 10 is supposed to be the height, but on this equation it's 9, so you have to take away 1 from the 10 and
You
make
can't
the
because there
h.
is no 10.
Well, you can add the 10.
Because look,
Okay, so you can
hold on,
do-
look at this one, look at these two.
This debate continues for 2 minutes. Eventually, one student revises her thinking, not because the teacher intervened, but because the students were allowed to own the reasoning themselves. But don't take my word, listen for yourself. Do you think this student now understands why it is h minus 1?
Then how does this one write?
Because you would automatically think that the height of each square is 10, but it's 9 in this equation, so you would minus 1 first, and that would equal 9
Oh, now I get
times
it.
4, because it would equal to this problem right here.
Oh.
So do you guys...
How does this expression relate?
To wrap this task up, the teacher asks students to relate the algebraic expressions they came up with to the pictorial representations. Notice how he asks a question to the class. Then he skillfully reads the room and decides instead to do a partnered turn and talk to make sure that all students are held accountable to reasoning about the question.
Basically 4 times 8, so that would be 40. And then it says subtract 4, so subtracting 4 would mean 36. So the original answer with the outside of the box.
So you're telling me 4 times 8, but h is 10, which equals 40, minus 4 equals 36.
To extend this task, ask students, what about different size square grids? Would the expression 4h minus 4 work for any height? Notice how the teacher uses the dot cam to make students' thinking visible to the class.
It works because you could, when you do 4h, it equals the sides times 4, but since you're repeating corners, then the minus 4, that will get rid of the corners that are repeated, and that will get you an answer for 5 by 5, which would get you 16, a 12 by 12, 44, and the 7 by 7 is 24.
Another excellent task for bridging the arithmetic to algebra gap is the formative assessment lesson representing the laws of arithmetic. Students will synthesize their understandings of arithmetic operations, properties of operations, and connecting expressions to the area of compound rectangles. While students match cards with expressions to cards with rectangles, monitor the room and listen to their discussions. This task can reveal a great deal of students' conceptual understanding and also engage them in productive struggle. Listen to these students as they make sense of an ambiguous scenario.
This will be the same thing. Look, it's 3 times 3 plus 4 times 4 plus 3 times 3, which is 3 to the power.
But then what about this square?
Yeah, it's 3 times 3. Oh. What? Yeah, it's 3 times 3, because look, this would be 3, this would be 3.
Right. Wait, how? No, 3 times 3, they mean it like 3 times 3, because that would be... What?
Look, this would be the length or something. Okay, so then that would go here, right? Because it's the same length.
Yeah, this would be 12 over here.
Well, yeah. That's 12, this is 9.
When you say that, what are you talking about?
That's the square.
What about the square? What measurement? Talking about area, perimeter, volume? Area, okay.
So,
All right.
So because of that, since this is the same equation too, 3 multiplied by 3 and
Wait, that would be 16. Here, is it one of these long ones? No. 3 to the second power is 9. So that would be like this one.
Yeah.
Plus 4 to the second power, which is this. Plus 2 times 2. What? Plus 6 times.
That wouldn't work.
Okay, so bring that one back. So 3 squared plus 4 squared. Where do you see that in the diagram?
Okay, this is 3 squared and this is 4 squared.
Okay, so you got the area of those 2 squares. So then you have to get the area of those other 2 rectangles.
Yeah.
Would it match with this part of the expression? 2 times 3 times 4.
Okay, 12. Yeah! No.
How?
No, it wouldn't.
2 times 3 times 4. How could 2 times 3 times 4 match
Because you do 4
the area of
times.
these 2 rectangles?
Could you do 4 times 3 and you do it 2 times?
What do you think? What would 4 times 3 tell you?
No, 4 times 3 would tell me the area of this one.
The area of that rectangle.
Yeah,
that
it
one.
works. Because you're multiplying it 2 times.
I think you got it. That was pretty cool.
Square 3, there is 3 squares, like she said. And when you do 4 times 4, there's 4 times 4 and then 4 times 4, 4 times 4.
Can I get a third student to explain what the 4 times 3 could be in that same expression? Go ahead.
The 4 times 3 can also be represent the length of the whole rectangle with the and you multiply the 4 with the whole total to get the whole total rectangle.
To close out this lesson, we attempt to make sense of the most challenging expression of all.
Is the 4 plus 3 is that as if this was an entire square there, 7 by 7, and that, but it's showing that the 2 times 3 times 4 subtracting, that subtracts the area that is there, which to get you your answer.
For additional support and resources, please visit GeorgiaStandards.Org, where you can find additional tasks, intervention materials, and more.